Hi, everyone. I don't know if everyone can see us and hear us, and just want to say hi and welcome to the Big Data meetup hosted by SmartCat. I'm Lola, I'm in business development, and I will be your host today. And we have Aleksandar and Predrag, who will be the presentation givers, right? So first of all, I would just like to say a little bit about SmartCat. So SmartCat is a creative data team, and we specialize in data science, data engineering, and DevOps. And this is something that we're proud of. We have all three under the same roof. And today, both of Predrag and Aleksandar, who are from SmartCat, will be telling you a little bit more about their expertise that they use daily during their working hours here. Aleksandar will be giving you a presentation on microservice patterns with Akka and Kafka, and he is actually a software engineer who primarily focused on distributed and data-intensive systems. And he started his career as a data scientist, but realized that a combination of backend and data engineering suited him better. So this is where he's at right now. And Predrag is going to be giving you a presentation on navigation in a 3D environment with reinforcement learning. And he is actually a data scientist at SmartCat, and he found a combination of programming, mathematics, and research in AI. And besides being talented and awarded, he is also seeking new knowledge and ways to improve himself. And he's also challenging problems that will push him out of his comfort zone. So in general, we at SmartCat love challenges, and we love finding solutions for those challenges. So without further ado, I'm happy to give Aleksandar the floor so that he can start his presentation. And I hope you enjoy today. Also, feel free to ask in the comments below if you have any questions during the presentation. Aleksandar and Predrag will both be happy to give you answers to those questions. So feel free. Thank you. Aleksandar, you can start.
Thank you, Lola, for introduction. Just to share a screen. Does anyone, or everyone can see the presentation? Hope it's true. Okay. So thank you, Lola, for introduction. And now it's my turn. So I will talk about some common streaming patterns that you may encounter while working on streaming and event-based architectures. So here is a quick agenda. So we are going to cover basics of Kafka, Akka Streams, and then I will try to show you how to integrate Akka Streams in your Kafka-based project and with some real-world examples. About me, just Lola already introduced us, but here you have my social media profiles, so you can contact me if you want. First question is, of course, what is Apache Kafka? It's a pretty hot project right now, and I will assume that a lot of developers are already familiar with the basics of Kafka, what it is, and some common use cases that Kafka can solve for you. So Apache Kafka is distributed streaming platform, and this is just a definition from official website. But in a nutshell, Kafka is just a message broker. It's distributed by design. It's pretty resilient and scalable, and it enables publish-subscribe messaging model. So Kafka is run as a cluster, and each node in Kafka cluster is called a broker, and every broker is identified by its ID. So broker is just a server or in a server that have Kafka node running on it. So Kafka cluster is used to store streams of records in something that is called topic. And you can think of topic as a database table, but without all constraints that comes with relational database table or Cassandra table. And every topic is identified by its name, and number of topics per Kafka cluster is basically unlimited. So you can create as many topics as you want. So now when we know some basic terminology of Kafka, what is broker, what is topic, we can review some more complex and some typical Kafka workflow. So here on the left side, we have Kafka producer, and Kafka producer is used to produce a message to a topic, and the topic is divided into one or multiple partitions, and partitions are distributed among different brokers or servers. And every partition is append-only log. That means that when producer produces a message to a partition, it will be put at the end of partition, and I already said that partition is append-only log. That means that partition is immutable, and once data is written to a topic, it can't be modified anymore. Kafka, I said that Kafka is pretty resilient, and resilience is something that is achieved by replication factor. And replication factor is just a number that represents number of your physical copies of your topic. And you can specify replication factor when you are creating a Kafka topic. And if you have, for example, replication factor of 5, that means that your topic will have 5 copies on a different nodes. Also, every message that is written to Kafka topic has incremental ID called offset, which is pretty important concept, and soon you will see why. Kafka messages are ordered, but this is true only for one partition, not across multiple partitions or the whole topic. So if your message is newer, that means that offset of that message will be higher, but only inside one topic. You can now, for example, you have topic with 2 partitions, and you have, and on first partition you have a message with offset 8, and here you can have a message with offset 5, but this doesn't mean that this message is newer because its offset is higher, because those 2 messages are on a different partitions. Data and messages in Kafka topics are kept for a limited amount of time, and it's configurable by a parameter called retention period. And by default, it's 7 days, but you can keep data in Kafka as long as you want, even forever. And when retention period expires, and your messages are removed from a topic, offsets will not reset. It will just, keep incrementing. Another interesting thing related to Kafka producer is that producer can assign a key to a message. So every Kafka message is just a key value pair, but can have some metadata like offsets or timestamps. But key is optional. So if you do not assign key to your message, key will be null, and messages with a key without key will be distributed in a round-robin fashion across topic partitions. But since Kafka 2.4 version, there is something called sticky partitioner that uses some more sophisticated algorithm than round-robin to distribute messages without key across partitions, but it's not important so much. On the other hand, if record has a key, that means that every message with the same key will end up to the same partition. So key in a Kafka message is not unique because it's more similar to Cassandra partition key. If you are if you know what Cassandra table is, it's basically just used to determine on which partition your message will end up. For example, let's say that we have some topic with 10 partitions where we are collecting data about temperature for some location, and we need those data to be ordered by location and in the same place. Then we should use something like location ID or location name as our message key. And in that way, we know that our messages for a specific location will end up in the same partition and it will be ordered. Also, partitioning of a key is done automatically by Kafka Producer API, but you have an option to implement some custom partitioner if you need to, and you can assign that custom partitioner to your Kafka Producer. So now, when we have data into Kafka, we need to read those data and to process it in some way and apply some business logic on that messages. And for that, we're going to use Kafka Consumer API. Kafka consumers are grouped into consumer groups. Each consumer within consumer group will read mutually exclusive partitions. So if you have, in this case, two partitions and two consumers in a consumer group, then each consumer will consume a single partition. But if you have more consumers in a consumer group than partitions, that means that's not a good case, because you will have some consumers that are not inactive. On the other hand, if you have more partitions than consumers in a group, then some of the consumers will have assigned multiple partitions to it. Consumers read the data from partitions sequentially, and after data is read, it's Kafka consumer should commit offset of that message. Unlike to the standard messages queue, it will just standard message queue will just delete the message after processing. Why are we using committing offset? Because when our consumer application dies, and if we restart it, it will automatically know from where should it continue to consume from a Kafka topic. By default, special Kafka topic is used to store your offsets, but also you can use some custom storage like relational database or Cassandra or MongoDB. And when your consumer crashed and you restarted it, it will just look to the offset storage, pick the last committed offset, and start to consume messages after it. Also, Kafka consumer have option to automatically commit offset, but it's not recommended, because in that case you don't have control of the message committing, and in that way you can lose data, and it's not a good case. So basically the best practice is to manually commit offsets after you process message or batch of Kafka messages. So just to sum up what we learned about Kafka. So Kafka is a message broker. It have 4 core APIs, producer and consumer API. And you here have a Kafka Streams and Kafka Connect. They are more high-level APIs, and they're built on top of producer and consumer APIs, but they're out of scope for this talk. And some common use cases is inter-service communication in event-based or microservices architectures. You can implement real-time data pipelines, ETLs, real-time integrations with Kafka, and you can use Kafka Streams to some more sophisticated stream processing. I think this was enough information for you just to get some basic knowledge about Kafka. And now I will talk about Akka, because our focus of this talk will be Akka Streams. And in order to know what Akka Streams are, first you need to know what is Akka and what Akka actors are. So Akka is a toolkit or set of libraries for building a concurrent distributed applications for Java and Scala. And Akka represent just implementation of actor model of computations for the JVM. Actor model is a pretty old idea, and it's popularized by Erlang programming language, which is used to implement highly concurrent and distributed telecommunication systems. What Akka offers us and why we should consider using Akka is a simple concurrency model. Basically, when you are programming with Akka actors, there is no need for complex operations like locking or synchronization. Distributed programming is pretty simple. So if you know to implement single node Akka application, there's no big difference to just distribute your actors and to make your application distributed out of box. And Akka also have a great fault tolerance mechanism because Akka actors are organized in a tree-like structure where each parent who is higher in hierarchy has control of its child actors. So just a simple example and explanation. So what is actor? Actor is just a structure, and it's a container for state and the behavior. And the state is, just state, like every application have some state, and behavior, which represent the way of the message handling. So I forgot to say that actors are, every communication between actors are done asynchronously by sending messages to each other. So every actor has a address and a mailbox. So these two actors send their messages to the actor mailbox, and this actor will just enqueue message from its mailbox and process one message at a time. And this is why we don't need a locking or synchronization mechanism, because actor will process just one message at a time. So there is no race condition. To sum up actor model. So similarly to object-oriented programming model, in actor model, everything, basically everything should be, nearly everything should be an actor. So as I already said, actors are communicated with each other between sending asynchronous messages. So every actor need to have an address in order to receive a message, and the actor can do on these four things. So basically, when actor receive a message, it can create a new child actor. It can send a message to another actor. It can locate some mutable state, and it can change the behavior for the handling of next message. And now, when we have a theoretical knowledge, I prepared two quick examples to help you to quickly get some patterns of how you can implement your actors. So imagine that we need to implement some cache with eviction policy. So example would be some hash map, and whenever we add some entry to the hash map, we will assign some timestamp to that entry, and after the period that expires, we should remove that from our cache. So it can be really hard to implement using, I don't know, play Java and Thread API, but with actors it's pretty simple. So the first step when creating actors is to define our protocol, and protocol represent just a set of messages that our actor can receive. So basically, we can receive insert message in order to insert our key value pair into our state. We can get request for some key. So when we need just to get to search our hash map by this key and return to our sender, and this is basically the actor who sends us messages. So we need the address of that actor to know to whom we should send our response. And this is evict message this is message that our actor is going to send to itself in order to know when it should check to are some entries in our hash map expired and should be deleted. And on the other hand, here we have our response protocol, and these are messages that our requester will receive. So we have apply function, which is used just to initialize our actor state. And this is mechanism that is used to schedule this message sending to ourselves. So basically, every second we are going to send to ourselves this evict message, and when we receive this message, we are going to remove all entries that expired. And the whole business logic and all complex stuff is encapsulated in this process method. And this process method will basically mark our initial state, and our actor will just, initial state will be just empty hash map. So this is our whole business logic. So we are reacting on 3 types of messages: insert, get, and evict. And if no one is familiar, this is Scala. I just forgot to say that because it's much nicer API than Java. It's much more friendly for developers. So when we get some insert message, we are just going to get what is the current time, and we will update our state from here, and we will set the new behavior. So we said that actor, when receive messages, it can modify some mutable state and set the next behavior. So how the next message will be proceeded. So when we create our new hash map with new entry, we will just set our new state, and when we receive next messages, we will have this new state. When we get this get request, we are going to search our state by key, and we will just wrap this to our value class that we defined here, and we will just send this to our requester. So basically, reply to is just our address of the actor who sent request for us, and this bang or tell method is used to send message in a fire and forget fashion to our requester. And we are not going to change behavior because our state is not changed. We'll, just behavior will stay the same as it was. And the evict message, so basically these 2 messages are sent from some client to us, from some external system, but this evict message cache actor will send to itself. So this is the message. Then every second we schedule sending evict message to ourselves, and whenever we receive this, we'll just filter out entries that expired, and just set that filtered hash map as our new state. And this is it. This is how you can implement some cache with eviction policy. And just imagine how this can be hard implementing in Java or in Scala, but using just the thread API. So basically, you will need to synchronize when you are inserting, getting key, and this eviction can be extremely hard. You will need to use schedulers. So as I said, Actor just provide you extremely simple API to deal with the concurrency. And this is how you can construct your actors. Basically, we will just create actor, and we are passing our eviction policy. So after 5 seconds expired, remove all entries in our hash map that are older than 5 seconds. We are using this tell method to write our data to the cache, and this is something new. So this is called ask pattern. So ask pattern is used to ask actor for something, and it will return a future of some response. And future is a construct, is Scala, that just represents some value that is detached from time. It's not available for you right now, but it will be executed on some other thread, and eventually it will be available. So onComplete is just a callback that will be executed when your future is completed, and this is just we are just printing the value that we get, and we are shutting down our actor systems. And I prepared one more example. It's also very similar but less complex. And after that, you will just spot the pattern how you structure your actors. So let's imagine that this is some IoT device actor that just represents some IoT device that will hold some air quality or some temperature data, and we can ask our actor for our current state, and our state is represented with this case class. Every actor will have ID, air quality, air temperature, and we'll just initialize our state here. And again, in a process method, there is whole business logic. we have 3 messages to react on: update air quality and update temperature. It's basically the same, just we are updating the value that we're getting from these messages. And when we get request for a state, we are just getting the reference to our requester, and we are just sending the message to our requester, and behavior will stay the same. It's simple, like the last example, and I hope you spotted some patterns. So basically, actor is just as I said, just a container for some state, and you can use it easily in a concurrent environment. This was a basics of Akka actors, and now I will try to introduce you to the Akka Streams. So Akka Stream is just a high-level DSL that is built on top of Akka actors. So that's why we need some knowledge of actors. And every one of us know what is stream. Basically, stream is just a sequence of elements that potentially can be infinite. And every Akka stream topology is composed of these three core components. So source, flow, and a sink. Source is just a component that have only output. It can have one or more outputs. Flows is a component that have input and output, or multiple of that. And basically the flows are those steps when we're just transforming our stream elements. And the sinks is element that can have only one or more inputs, and it's just a termination point of our stream. So let's see how you can implement simple stream topology with Akka Streams. First, you will need a source, Akka Stream source, and we can create source from any Scala collection. We can create source from Scala futures, from HTTP requests, from Cassandra tables, from JDBC tables, from Kafka topics. You will see later how to do that. Then we are defining our flows. So basically we have some list of tweets. We just want to remove the hash. We just want to transform every tweet to a lowercase and just filter those who are longer than 3 characters. And our sink is just a dummy sink that is going to print every element it receives. So when we define our stream components, we need to wire them up to connect them. And to connect them, we're going to use via and to methods. So basically, via method is used to connect source and the flow, or flow with another flow. And to connect source and flow with sink, you are going to use to method. And when you connect all your components, what you're going to get is something that is called a runnable graph. And runnable graph is just a blueprint of our stream processing topology. It's totally lazy. It won't do nothing, but if you want to execute your stream and start processing, you need to invoke this run method. And only when you invoke the run method, the stream will start. Of course, you can use this builder style API, and basically it's the best practice to use it like this instead of, you know, just defining every component separately. So why you should use Akka Streams? It has declarative API, as I already said. It also has a lot of operators that you will need just a few seconds to apply them. But if you are not using Akka Streams, it can be really hard to tackle with those tasks. It has a great integration with other systems via Alpaca project. Stream supervision is great, like in Actor API. And the most important thing is that Akka Stream topologies are back pressure aware. So there is no need for you to write any back pressure handling code. Now, just a quick review what back pressure is. So imagine the situation when you have downstream components like a consumer that is slower than upstream components, And over time, your downstream components will be overwhelmed by the messages that are coming from our source or some producer or any upstream component. And when your pipeline is back pressure aware, that means that downstream components will send notification signals to upstream components that they are ready to process some elements. So, for example, this consumer can process only 5 messages per second, and this producer sending pace is much more than that. So this consumer will tell to this producer, I can only process 5 messages at a time. Please give me those messages in a batch of 5, and that is how you save your consumer of crashing. So how back pressure is implemented in Akka Streams. So I said that every Akka actor has its own mailbox. So as actor has a mailbox, every stream component has its own mailbox. It's some queue that is used to buffer elements, and it's unbounded. So basically, it's just bounded by our server memory. Just if someone is interested how back pressure in Akka is implemented. But sending signal between downstream components to upstream components, it's done automatically, so you don't have to do that. And we're coming to the end. Basically, what is Alpaca? Alpaca is some open source initiative which goal is to provide Akka Stream API in order to write application to connect multiple systems with Akka Streams. So it's similar to Kafka Connect or Apache Camel if you work with that, but it is not configuration based. It will just give you a bunch of sources, sinks, and flow for different systems. So it has support for major cloud providers like AWS, Google Cloud Platform, or Azure Cloud. It has a great integration with standard data storages like relational databases, Cassandra, Mongo, Elasticsearch, HDFS, and great integration with some standard messaging protocols like JMS, Kafka, or MQTT. And I don't know if we have much time, but I prepared a few examples, but I think we'll just have a time to cover this one. So this is a pipeline that can be pretty complex if you are using a plain producer and consumer API. This pipeline is used to consume some ratings from bookshop website and to write to process it in some way and to write those records to Cassandra with at least once delivery semantics. So we are using Alpaca Kafka connector for Akka Streams. We need just to provide some consumer settings. So basically URL to our Kafka cluster and our consumer group. And the second parameter will be the topics that we want to consume. So I said that Kafka messages are key value pairs. So here we are just going to extract the value because we are not interested in a message key. I'm using the Avro message format for Kafka. So here we are going to have Avro message, but we want to transform it to our domain model. Then we can parallelize our stream by applying some business logic to our rating. And here we are using Alpaca Kafka connector to just write every message that we receive from Kafka to Cassandra with, I already said, with at least once delivery semantics. And this is really strange line, but I can explain this. This is used to commit offsets. So basically, after all of this processing, you will want to commit your offsets in order to know from where you should continue to consume your messages when your consumer is down. And this is it for me. I will share this presentation because I have a lot more examples, but I don't have a time. but I have source code on a GitHub and a little more explanation of this, so I will share that with you later. So does anyone have any question?
If you do, feel free to put them in the Zoom group chat and we can...
Yes, yes, of course.
If not, we can move on to Predrag. So thank you very much, Aleksandar. It was a very insightful presentation. We move on to Predrag to talk about a completely different topic. So Predrag, would you like to introduce to us what you have?
Of course, just a second. Let me share screen. I hope that everyone, that you can see this. So basically, yeah, greetings from my side also. We are going to shift topics here a little bit from an engineering talk. I'm going to give you somewhat talk more research oriented or scientifically oriented. And I'm going to talk a little bit about reinforcement learning, what part of machine learning is this kind of learning, and how does it connect to 3D environments and navigation as a problem in a 3D environment. So Lola already introduced me at the beginning. My name is Predrag Negvanovic. Once more, I'm a machine learning engineer at SmartCat, and here are some of the contacts where you can reach me: my email, LinkedIn, or even GitHub. And I'm going to start with a little overview to present you what I'm going to talk about this in today's presentation. I'm going to start with a little bit of an intro to reinforcement learning from a business perspective for you guys to see where is reinforcement learning in today's world, some of the use cases, short history, and the main loop with the concepts. And we are going to go over 3D environments as an example, and to see our example and what are some of the tips and tricks for its implementation. So basically, reinforcement learning from an economic value or economic perspective in today's world, I'm going to quote Andrew Ng from 2017 presentation. I'm going to show you economic value of different kinds of learnings in machine learning from decreasing order. So the first is supervised learning, and most of you who are into this industry or into machine learning knows that most of the projects and most of the business value is gained through a supervised learning, simply mapping an input A to an output B. And the most problems are usually in this domain. The next is transfer learning. I'm going to explain you later why is this like so, but for now, keep on with me. Next is transfer learning. We already have our predefined models, pre-trained models. We are going to train it additionally for some of our use cases and use it like that. We have unsupervised learning, and at the bottom, the last one is reinforcement learning. So as you can see, reinforcement learning is not appearing so much in the industry, at least from a business perspective. And actually, this quote is true. It was back at three years ago, but I think it still is. The excitement in PR value is contrary to the economic value is reinforcement learning is creating today, because I'll try to explain why is it so difficult, but why is it so difficult. But the most challenging part is generating data and gathering data for reinforcement learning algorithms and the state of the algorithms itself. But what is reinforcement learning? Through one sentence, I can tell you that reinforcement learning is goal-oriented learning through interaction with the environment. And I would expand this sentence by saying that the goal of reinforcement learning is to find an efficient way for machines to learn, to be able to solve some significant economic or mathematical or some kind of tasks with computations and analysis. So basically, it's pretty different from traditional machine learning, where we are learning from experience. But if you think about it, it's more like human learning, because humans are in everyday lives interact with environment, and they are learning through interaction with that environment. Some of the use cases, I mostly took this from OpenAI and DeepMind study groups, and there are presentations. Usually they're like tasks which are solved by robotic hands, or like this stacking stones, or even solving a Rubik's Cube. We have turn-based games that we can that can be played through reinforcement learning, or even multi-agent games such as Defense of the Agents, where you can see collaboration of agents, or even hide and seek, which is it was back last year. It was the latest research from an OpenAI. Even SmartCat, we have a totally different domain. It's not robotic or video games, but it's like temperature optimization for HVAC devices. It's our own Optimus Power. So I just want to give you a perspective what some of the use cases that you can use reinforcement learning for. And now you may question yourself, why mostly robotic simulations and video game simulations? The reason is back to that quote that I put. It's actually a problem of generating data. Only these kind of simulations can create enough data for agent to be able to learn to solve tasks successfully or something like that, because in real world we cannot create some mechanical structure to be able to have that kind of numerous attempts, or to be able to generate enough data in one place. And simulations are way to go. And basically today research is mostly through these simulations. I'm going to give you a short history overview. We're going fast through it, just you can see what are the roots for reinforcement learning. And we have two tracks actually. We have optimal control track, which is kind of mathematic oriented, and we have a trial and error, which are more like into psychological psychological roots. So optimal control started back in the 1950s, and it's actually minimizing dynamic behavior of a system. It was started by Richard Bellman, which is a quite famous name in this area. So if you're starting with reinforcement learning, you will hear about Bellman's equation. And he introduced a concept such as system state and value function. And value function actually is a Bellman equation. Actually, optimal value function is a Bellman equation, which is represented as an optimal return function. He also introduced concept of a reward. And if you want to mathematically describe this kind of system, we will use MDP, which stands for Markov decision process. And trial and error on the other side, as I said, has roots in psychology with a focus of animal learning. Basically, we have two concepts. It's selectivity and associativity. So we want to select an action to apply on something, and to select the best result out of it. It was boosted with temporal difference learning in the 1980s of Richard Sutton. That was he's one of the fathers of this domain, and it was only based in prediction-based problems. So we have a merging of these two ways back in 1989 into one learning. In one algorithm that was called Q-learning by Professor Chris Watkins, and from that on, this was a starting point for reinforcement learning to come to what it is today. Now I want to show you some basic concepts or the main concepts about reinforcement learning, and the main things you will see when you type in your search engine reinforcement learning is the main learning loops. So the main protagonist in our main learning loop is actually an actor. actor is someone who is trying to achieve that goal. I said before, it's an entity. It can be a software agent, or it can be some hardware mechanical part, which is actually running in an environment. Environment can be, as I said, robotic simulation, video game simulation, or even a real world environment in which we put some mechanical agent. It applies some actions in this environment. In return, it gathers some observation. By observation, I mean state of the environment. It can be some visual states, such as image, or it can be some numerical state, whatever we describe state with. And it gets reward. Reward is always a numerical represented number. It's always numerically represented. And why is that important? Because we want to define our goal, and our goal is represented with a cumulative sum of rewards. It can be a maximum reward or it can be minimum reward. It depends what we try to achieve. And how we get to that goal is by creating something that is called an optimal policy. Imagine policy as a way of choosing an action to get to a certain state. An optimal policy is basically choosing an optimal actions to get to our goal. In a mathematical way, we would say that policy is a function of probability to be able to choose a best action to reach our maximum reward or our end state or our end goal, for example. And we have something called value function. I already told you that was introduced by Richard Bellman. Value function actually describes, it gives an each state a value. It's a numerical value, so we can value how much a certain state is valuable. That's really important. So we know which state is more valuable, we would go to that state. And also we have action value function, which scores each action, each applied action to each state. So with this function, we can evaluate how our action is valuable, really. So if we know what are the most valuable actions, we can choose those actions and go to those states and find our optimal policy. And that's basically, that's it. It sounds very simple, but it's really, it's hard to achieve. Solving one of these functions yield us an optimal policy. And that's the point. But the problem is that if we want to solve this system of equation numerically, it's really time consuming, and it depends on the multiple look ahead searches, which is not really what we want, and it's not really doable. So when something is not doable numerically, we try to approximate it. And when we are approximating an action value function, that is called a Q-learning. And later people try to approximate the function of probability itself, and that's called a policy gradient. And these two are the basic groups of methods in reinforcement learning. And you already can conclude that if we are trying to approximate something, maybe we can use something as a ultimate approximator, which is neural network, and voila, there's a connection with machine learning itself. So how connection with deep learning actually occurred? Well, occurred 7 years ago, back in 2013, when a research group from DeepMind, they published a paper called Playing Atari with deep reinforcement learning. When they used the Q-learning actually, and they approximated with neural networks. Actually, that was convoluted neural networks, and that was a kind of a boom. They published it at NIPS, which is the main conference in this machine learning area, and even at the Nature magazine, which is the most important magazine in the science in the world. And they even achieved that they showed achieved above human level performance And that's the point where reinforcement learning exploded into a research-oriented field, and many teams in today's world are working on reinforcement learning, and that's why it is mostly researched area. And people are usually dealing with simple 2D environments, usually with Atari games or balancing a karting pole or Super Mario or Sonic even. But when they solved all the problems with the 2D environments, they step over to 3D environments, and 3D environments were like first-person shooters such as Original Doom, where you have yearly competitions, and you can see you already have shooting and moving, etc. Or even DeepMind, they open sourced their DeepMind lab with maze-like structures in 3D space or space tag games, etc. And then problem of environment control occurred. And what is environment control actually? Well, it's trying to solve a navigation through visual input. So we are trying to move our agent through these environments by visual signals, and that's not something very easy to achieve. And I have problem like to solve in environment that I choose myself. It's obstacle tower environment, and last year that was actually a challenge. It was yearly challenge by Unity and Google Cloud Platform collaboration. Unity published obstacle tower environment written in Unity engine, and it was a really nice looking environment, and it was the most beautiful actually till that time. It was a complex environment with a real-time lighting and shading effects, and the obstacle tower as environment itself is it follows an agent in a third person perspective, going through a series of rooms in a maze-like structure where it should solve some puzzles and learn to navigate, to pick up some time orbs, etc. And the environment itself, it had 24 floors when I started. Now it has 100, and it was published to challenge the tackle problems of generalization and control and problem solving with reinforcement learning. It's mainly oriented towards the researchers, but it was challenge itself. So a little bit more details about environment. Our state was actually a visual signal. It was a pixelated image with 3 channels, RGB image with 168 by 168 pixels. We had multi-discrete action space. So we had like up, down, left, right, jump, no movement, turn left, turn right, counterclockwise, etc. So when we flattened, we make all combinations 54 actions, and we have rewards, and rewards are only given when we are passing through a door. It's actually passing, when we are finishing floor, it's 1 point, and passing through a door between a multiple, if a floor is with multiple rooms, then it's 0.1, and we'll see how that affects our problem later. I choose for training algorithm, I choose state-of-the-art algorithm. By that time, it's called proximal policy optimization algorithm. It was open sourced and published by OpenAI. It was a gradient policy gradient algorithm, and it updated the policy based on trust regions. So basically, very simple. Its update step is a ratio of a new and old policy. So basically, you're always trying to follow a good policy, never diverging too much. And that was a really nice feature to have for this algorithm, because it allowed multiple updates per one training step, and that allowed the utilization of data better. And it was improved version of algorithms that came before it actually. And it was for me, it was natural thing to go with the state-of-the-art algorithm to try to implement it. And this was the architecture of my neural network model. Basically, I had a three-layer convolutional network, followed by a linear flat and dense layer. And since I knew that I had to follow the history of movement of my agent, I knew that I should put a recurrent neural network append on it. Some earlier approaches were stacking frames, but this wasn't enough here. So I opted to go with a recurrent neural network with the shared parameters, and at the end we would yield the policy. This is noted with PI, and also value function. I forgot to say that I implemented this BPO algorithm in an actor-critic architecture fashion. That means that our actor is policy, and the value and the critic is a value function. And value function actually just is here just to be able to lower the variance of our policy function. And that looked like this, and it wasn't. This wasn't what I hoped for. Our agent was just running in a circle, and that was kind of bad. Or if I tried to play it like this, this was another policy, and this was also bad. You can even leave the starting area. So I tried to figure it out. Okay, what can I do? Because maybe I can use some additional data for reward shaping, so we can define our reward function. And I tried to use time as additional constraint. So I tried to punish an agent because we have in-game time, and time is filled whenever agent solves or finishes a room or pick up some time warps. So if he doesn't do that, let's try to punish him. And it ended up like this. So now it doesn't move at all. And what happened here? Well, you heard of existence is a pain sentence. That's basically it. When using a time as a reward, it's like a double-edged sword. You have to be careful because agent is penalized in every time step, so it's painful for him or it. So the best way to stop the penalty is to let time run out as fast as it can. And another question was, is our model complex enough? But eventually I saw that model complexity is not important at all. It's not like traditional machine learning. You can put a numerous or an additional layers, but it's not going to achieve a better performance because we extract already features with 3-layer convolutional neural network. It's not going to work any better with it. So what's really important in reinforcement learning is to monitor your training procedure, because visualizing metrics and tracking them can tell you really a lot about what's going on. Everything's fine when algorithm works, but when it doesn't, you should implement some kind of visualizations to see why it's not working. And with reinforcement learning, that's not really an easy thing to do because you're having multiple components of a loss function, because every algorithm is a loss function. And how can I interpret this, for example, policy loss? Is it a good thing to be able to be between 0 and -1, and or is this a good entropy function? And that was a hard thing to learn. But for example, this was a really important thing. This entropy function actually give agent that trade-off between exploration and exploiting the good actions. And as it turns out, the entropy, for example, should have a high values at start, because agent is using random actions, and through a time it should slowly decrease because the agent is getting to know what are the good actions, for example. So that was a thing to learn. And the problem was actually sparse rewards, because trajectories between start point and ending some floor there is a lot of steps, and if you are not getting a reward in each step, how do you know which is the best way to go to end the room? Sorry, and I knew I had to invoke some kind of inner reward system for an agent. So I tried to see if that was something that people already did, and it turns out there was something called inner curiosity model, intrinsic curiosity model, and it was a system for giving an inner reward system for an agent. It's actually really simple. It's trying to give an agent a push to try to explore unseen states, and you're trying to extract feature for a current state, ST, and the next state, ST plus 1. Then you're trying to predict already extracted features, and when you subtract the vector of features for next state and predicted next state, you get a value that is an inner reward, and the agent will explore new states. Now that's not ideal way for this problem, because you want agent to just go through a door and end the room, but it did help actually, and you'll see how did it help. Okay, it's not an ideal movement, but it's a lot better than not moving at all. And agent is actually going through rooms, and it's actually passing through and finishing rooms and going to another areas, which is kind of nice. And that was my hypothesis, and I'll explain you now. It can be better. It can be better, but why it isn't? Because I put some additional constraints when training. Actually, I had constraint of lacking of data for reward engineering. I had just the time, and I think that's not enough for a good reward function to encapsulate all domain problems. I made this problem episodic. That means that after a certain amount of steps, I set an end state and restart all environments. And that's a limiting factor because this is a continuous problem. We have a numerous of floors. And we have some of texture glitches of environment itself. I don't know how does that affect CNN and feature extraction part. Because this was a challenge, there are blogs of people who ended up in first 3 place or 4 or 5th, and which techniques they used. Generic one is tuning hyperparameters, and I have to tell you that if you're using an open source variant of some of our algorithm, if you're not implementing it yourself, you'll still have to tune hyperparameters, and reinforcement learning is really sensitive to hyperparameter tuning. It's not like traditional machine learning, and even 0.001 in learning rate can lead to your algorithm diverging. The next is imitation learning technique, where you can, the name speaks for itself. It's like imitation learning. You tape yourself playing the game and leave it and show agent that or you connect actions with states and turn the problem into supervised problem, and that's how an agent can learn additionally. Or use something called child divergence instead of entropy loss for that exploration versus exploitation issue. Or use behavioral cloning technique, which is you tape yourself playing a game for a couple of minutes, and you use that as a supervised learning method for your agent to learn what's a good way of playing the game, which is actually not that, which is actually good, because this was the first place. This was a winning solution actually. And what are tips and tricks during the implementation if you're choosing to implement your own and not use some already open sourced ready algorithm? I used an observation normalization before before training. Actually, I sampled 10,000 visual inputs, and I found mean and standard deviation. And during each training step, I used to normalize the observation. It helped the training. I use scaling of internal reward because they're non-stationary, could have variance, etc. So we used to normalize it. This was the thing that struck me the most because it was implemented in, if you're trying to look at some implementation on GitHub, at every algorithm, every implementation has a custom initialization of networks. Usually when you're trying to implement some project, you usually are importing a model from Keras or TensorFlow, and you wouldn't supposed to change initialization, you use custom initialization. Well, in this case, you will have to do it. And some training tips, learning rate decay. During time, you should decay your learning rate because agent is learning what are the good actions, so it shouldn't explore that much. So if you decay your learning rate, it can help. Again, hyperparameters tuning, I already told you about it. And something called experience sampling or not to sample. It depends of algorithm that you choose. If you're choosing Q-learning, then you can sample experience. Experience is like cache of your observations, states, etc. And you're using it when you're running a batch training. And if you're using a Q-learning, then you can sample, but if you're using a policy gradient method, then you shouldn't sample because that will mess up the training. And that's something useful to know about when you're starting with this. And finally, the key takeaways from this research and this project and reinforcement learning as a field in general is that it actually requires a lot of expertise, and it's math heavy because it requires a lot of build-up knowledge and a lot of research. If you're trying to deal with some cutting-edge problem, if you're trying to solve something that's latest or interesting, expect to read a bunch of research papers and to expect to see a lot of maths. And the problem is that a lot of expertise is stored in-house groups such as OpenAI or DeepMind, and some kind of engineering and implementation tricks are not mentioned in papers. And that's actually the most painful thing, because if you're starting with a statement, for example, okay, they implemented this problem, they solved it in their paper and they published it, I can do it also. You're about to have a negative surprise because paper results are very hard to reproduce because of implementation tricks that are not even mentioned in appendix of research papers. You have to come up with it yourself. You'll learn the hard way. And the next steps in reinforcement learning, well, usually, of course, 3D environments and multi-agent environments and multi-agent collaborations such as defense of the agents or something like that is the next steps in reinforcement learning. And that's about it. Thank you very much. And if you have any questions, I'm here to listen and to answer them.
Thank you, Predrag. So yeah, feel free to use this remaining time to ask any questions in the group chat. If there are no questions in the meantime, I wanted to let you know that Aleksandar shared his presentation in the group chat as well, so you can access it there. And you can also access Predrag's blog. I will share it with you now. So you can feel free to also read it if you're interested, to have it in writing. And yeah, this concludes our sharing session. Thank you, Predrag and Aleksandar. I just wanted to mention that we actually share these things in our company every week, but this time Aleksandar and Predrag decided to share it with you guys as well. So I hope that you enjoyed it. And yeah, if there are no questions, then this concludes the session. Thank you for coming, and thank you for giving us your ears for an hour or so.
Thank you also from my side. I hope you had a good time.
Yeah. Thanks, everybody.
Bye.
See you next time, hopefully.